Another way to derive a Taylor series from a function is using what's called this list of elementary functions. So these are some basic functions and the Taylor series to which they can be converted. And you also see here listed the interval of convergence for each of them. Now this one right here with the star on the 1 plus x to the k has a plus or minus depending on the value of k. So it may, there may be some greater than or equal to or less than or equal to there if, depending on what your k is and what happens with that, even or odd kind of stuff. So let's look at an example. It says find the Maclaurin series for f of x equals e to the x squared over 2 using the list of elementary functions. So if I look at the list up here, I see that e to the x by itself goes to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on and so forth. And that's equal to the sum from 0 to infinity of x to the nth power over n factorial for x, between negative infinity and infinity. So interval of convergence is infinite. So e to the x squared over 2, I'm just going to take this and I'm going to replace the x with x squared over 2, just like if I'm finding f of x squared over 2. So I'll have x squared over 2 to the nth power divided by n factorial. And then to clean that up a little bit, I'll have, x to the 2n when you raise a power to a power, and then moving the 2 to the nth power down to the denominator, I'll get x to the 2nth power, and I'll have 2 to the nth power n factorial, and it'll have that same interval of convergence. Another example would be this one. It says find the Maclaurin series for f of x equals natural log of x plus 1 using the list of elementary functions. So if we go up to the natural log of x, we get the natural log of x is x minus 1 minus x minus 1 squared over 2, so on and so forth. And with this one, the natural log of x, I'll just write that out so we can see it on our screen. 1 to infinity, negative 1 to the n minus 1 power, x minus 1 to the nth power, all over n. This one is convergent for x between 0 and 2. And here you have c equals 1 because we have x minus 1 to the nth power and r equals 1. Now with this one, we want to be a Maclaurin series, so we want our c to be 0. So hopefully when we plug in the x here, that's going to take care of it. Otherwise we might have to do some adjustments. But the natural log of x plus 1 would be the sum from 1 to infinity of negative 1 to the n minus 1. Notice the n's don't change. Here we get x plus 1 minus 1 to the nth power. So wherever there was an x, there is now an x plus 1. So this one now is a Maclaurin series centered at c equals 0. So c equals 0, the r is not going to change, that's still going to be 1. So the interval of convergence would be negative 1 less than x less than or equal to 1. It's centered at 0 with a radius of 1. So 0 give or take 1, and the right endpoint is still included. So you can see how you can adjust from an elementary function to something similar using parameters. You can also combine some of the elementary functions like e to the x and arctangent of x. So if we look at our list, you can see that e to the x, of course, is that 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on and so forth. Arctangent of x from the list is x minus x cubed over 3 plus x to the 5th over 5 plus, minus x to the 7th over 7, so on and so forth, plus x to the 9th over 9. And so this one ends up being the sum of negative 1 to the n times x to the 2n plus 1 over 2n plus 1. So with this one, it just says to find the first three non-zero terms. So f of x, which is e to the x arctan of x, I could take these two series and multiply them. And I only need the first three non-zero terms, so I'm not going to need every single term. I can just kind of start foiling things out and figure out which ones have the highest power. So if I take the 1 and multiply by everything, I get x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. Okay. When I distribute the x, I would get x squared minus x to the 4th over 3 plus x to the 6th over 5. You see how it's filling in those terms that are missing. When I multiply by the x squared over 2, I would end up getting x cubed over 2 plus, or minus x to the 5th over 3, or no, the 4th over 3. Sorry, I'm multiplying by x squared. Actually, that should be x to the 5th over 3. And then I would have plus x to the 7th over 5, and so on and so forth. And so you can see that what's going to happen is this is the last time I'm going to get these powers, because when I start multiplying the x cubed, this automatically becomes x to the 4th, and so on and so forth. So you just kind of need to go out enough to where you've gotten the first 3 powers here. So I've got x squared, and x cubed, and that's all I really need, so I don't need to go any further. So I would have an x, I would have minus x squared, and then I'm noticing that I've got minus x cubed over 3 plus x cubed over 2. So 1/2 minus 1/3 is, of course, 3/6 minus 2/6, which is 1/6. So then I would have plus x cubed over 6. And if you needed to go another term, you would just multiply the next term in the list, and then you would add up the x to the 4th. But all it asked me for was the first 3. So that would be the first 3 of those. I've just multiplied those things by distributing them. And then finally, this says use a power series to approximate the value of the integral from 0 to 1 of e to the negative x cubed dx with an error of less than 0.001. So if I'm looking at the power series for e to the x, that's 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So if I am plugging in negative x cubed, I'm just going to replace the x with that. So I get 1 plus negative x cubed plus negative x cubed squared over 2 factorial plus negative x cubed cubed over 3 factorial, all the way down to plus negative x cubed to the nth over n factorial. So what's going to end up happening with that then is you can see that you're alternating your negative 1 to the n, and everything else is just going to come out with those n's. So that gives me the sum from 0 to infinity of negative 1 to the nth power. We'll have x to the 3n, because you would raise a power to a power, and then n factorial. Okay, so the integral of that if you integrated term by term, the integral of 1 would be x. Here you would get minus x to the 4th over 4. Here you would get, this one would end up being x to the 6th, so we would get x to the 7th over 2 factorial times 7. With this one, we would have x, negative x to the 9th, so that would be minus x to the 10th over 3 factorial times 10. And then so on and so forth. And for the nth term, we would have negative 1 to the nth power. That's not going to change. We would have x to the 3n plus 1 divided by n factorial over 3n plus 1. So that's going to be our series. Okay, we need an n, capital N, such that the absolute value of a sub capital N plus 1 is less than 0.001. So let's calculate that absolute value of a sub n plus 1. That will be negative 1 to the n plus 1. Well, don't need that because we got an absolute value. It's always going to be positive. And of course, we don't need the x part of this because this is a power series. So we'll have 1 over n plus 1 factorial times 3 times n plus 1 plus 1. So that is 1 over n plus 1 factorial times 3n plus 4. And we want that to be less than 0.001. Now, in order to make this work, I need to figure out how to make, because this would be like a cross multiply situation, I want that n plus 1 factorial, if I multiply on both sides, this one ends up being on the top here, and the 1 over 1.001 ends up being on this side. So I would have n plus 1 factorial times 3n plus 4 greater than 1 divided by 0.001, and of course that is 1,000 if you put that in your calculator. Now, solving an inequality like this is not super easy if you need a precise decimal answer, but we don't. We want an integer, or actually a whole number. So what I'm going to do is I'm going to actually just calculate out the first couple of values of n and see what happens and how long it takes me to get a number that's bigger than 1,000. So for n equals 2, n plus 1 factorial times 3n plus 4, if I just put that in my calculator, I get a 20, and that is not bigger than 1,000. So we're good. We're not good there yet. If I plug a 3 into this, that would be 4 factorial times 3 plus 4, and that gives me 312. So again, not bigger than 1,000. But if I plug in n equals 4, I get 2,280. It would be 5 factorial times 12 plus 4, so 16. And that is bigger than 1,000, so that is what I need. So I need it to be at least 4 terms. So what I'm going to do now then is I'm going to say the integral from 0 to 1 of e to the negative x cubed dx is about 1, that would be n equals 0, minus 1/4, that would be n equals 1, because we're looking back at the formula for e to the negative x cubed. Plus for n equals 2, we would have 1 over 2 factorial times 7. For n equals 3, we'd have minus 1 over 3 factorial times 10. And then plus 1 over 4 factorial for n equals 4 times 3 times 4 plus 1 is 13. So again, I'm going back to this thing that I found as the integral of e to the negative x dx. I'm just calculating out the first 4 terms of that and using it to approximate. So you can plug this in and figure out what the answer is numerically, and that would give you your approximation from 0 to 1 of e to the negative x cubed dx. That's pretty simple. It's just arithmetic. I'll let you do that one.